Hello everyone, this is Professor Delagrammatikas, and today's lecture really attempts to solidify a lot of the concepts that we've been talking about regarding design optimization and how we could apply these basic concepts of calculus to systems engineering, to the design of thermal systems that we've been looking at in this class so far. So what I wanted to do first is take this golden opportunity to try to innovate, try to experiment a little bit with you, and have a distance learning, almost an online learning lecture that allows us to reinvent at least just a little part of how we deliver learning and how we deliver education here at Cooper. So that's the first part. And the second part that I want to ask you to do before we get started is to launch MATLAB on your computer, and to make sure you direct your path to the following. Just go to your Steam table bundle that you downloaded from the Moodle site and go to the following path where you have bopt intro. And those are the subfolders in there are the ones that we'll be looking at throughout the demos and the hands-on tutorials, the guided tutorials that we'll be looking at today in this lecture. So first I want to break this lecture up into two main parts. The first is I want to look at the terminology. I want to define some of the nomenclatures, some of the words that we've been using. I want to formalize those and formalize the concept in the context of the ideal reheat ranking cycle that we have been studying for the past 2 weeks. Next, I want to I want to analyze, I want to solve some very basic analytical problems just by hand, things that I'm certain that you've done years ago, but I want to bring those back into your recent memory and then use those as a foundation to develop generalized problem formulations. I want to come up with the equations that will be used not by you technically, but by the MATLAB optimization toolbox. I want you to know what's going on behind the scenes, if you will. And the function that we're going to be using in MATLAB is fmincon. It's a minimization function that has constraints, fmincon, and f is what's known as the objective function. Next, we'll be doing an in-class exercise where we'll be programming solution methods. We'll be looking at the different types of functions that we have to create in order to utilize this toolbox. So let's begin with the ideal Rankine reheat cycle, where we looked at the pressure ratio to maximize thermal efficiency. And what we did by hand was we looked at the different points in the cycle. We have a first turbine from point 1 and 2, where we extract work from the steam, the superheated steam, and then from 2 to 3 we reheat, then again extract through a different turbine from 3 to 4, from 4 to 5 we pass the stream through a condenser and then pump from 5 to 6 so that we can let the steam flow, the subcooled water flow through the boiler until it's reheated back to the superheated state at point 1. Now, the problem asked us, if we have a constant maximum temperature, the turbine inlet temperature at points 1 and 3, what happens to the thermal efficiency of the cycle if we vary the pressure to which we expand to point 2 and thereby point 3? If we shift this curve from 2 to 3 up and down, what happens to our thermal efficiency? And what we were also able to find out, we calculated with our own simulation, was the rejected heat, the heat rejected from 4 to 5, and also the heat added from 6 to 1. And what I wanted to do was think about what would happen if we didn't have an automated routine. What we did was we looked at the different pressure ratios. Pressure ratio is P2 over P1. And somebody told us, hey, start at at a pressure ratio of 0.2. So we calculated that. And as designers, what did we think we should do after that? Well, we have a range a pressure ratio range within which we can operate, so we decided maybe we go to 0.1, maybe 0.9, and use our function 2 more times, just to increase our understanding, our knowledge of what's known as the design space. And remember, this is still at a constant T1 and T3. We're looking at just one T1 and one T3. And so we decided, well, this simulation works quickly enough. Instead of trying to come up with any other routine, let's just brute force plot as many of these points as we can and see if we can come up with a relationship. And that's really what we did. By brute force, not only did we change the pressure ratio, but we also changed the inlet turbine temperature and determined that the efficiency varies in such a manner as we see on the screen. And we recognize that maximum efficiency occurs when you have maximum temperature into the turbine and also a pressure ratio at about 0.2, 0.3. We can rotate this graph around and really pinpoint it visually. But then we thought to ourselves, that's not how things work. Yeah, if this were an unconstrained problem, we would have no problem solving for the maximum efficiency, both the value of the efficiency and the location of the efficiency in that design space. And we looked at it from a different angle and said, hey, wait a second, if we change the temperature to which we allow our steam to get to before the turbines, there's a very interesting relationship between the location and the values of the optimal efficiencies in that case. And we see that at a lower temperature, we want to have a higher pressure ratio. In other words, that the pressures get closer and closer and closer to each other as we decrease that temperature. And so what I want you to do for the next time, it's going to be a very quick problem to solve, is just take these 5 points that you see in front of you, and you don't have to do anything special to find the maximum points on each one of these curves. Just look at the graph here, and for each of these points, just take the pressure ratio and the associated temperature. The temperature at the bottom is 800, then the green one is 850, 900 is the middle one, the red, 950 is that teal blue color, and the topmost is 1000 Fahrenheit. And you can convert these numbers to kp into Celsius and the pressures to kPa. I really don't mind. I just want you to take these 5 numbers, take the pressure ratios and the temperatures, use the simulation that we wrote and that you developed, and draw up TS diagrams. And I want you to come up with some type of understanding as to why the optima exist where they do. Why does that happen? Does it have to do something with the curvature of the enthalpy curves? I don't know. You have to figure that out. And so I want to now pose some what-if scenarios. What if we didn't have the luxury of an unconstrained problem as we very quickly were able to solve before? What happens if the boiler itself couldn't give us more than, let's say, 3,350 kilojoules per kilogram? What would you do? In this case, we have the output graph of the added heat input to the system, and if we draw our line at that constraint, then everything above that line is no longer inside what's called the feasible design domain. We've constrained that domain so that we have fewer possibilities of getting to that the optima that we saw before. So what happens in this case? Well, the way I look at it, I'm going to show you a couple of solutions. The way I look at it first is I take each of these temperature lines, and where they intersect with that heat added constraint, I just draw a line down to pressure ratio. Blue for blue, green for green, red for red, etc. And remember that as we move toward the right, these are increasing temperatures. Okay. Then what I did was, with these 5 lines that we have here, I just transposed them over to the thermal efficiency graph that we saw a long time ago, and we recognized, well, what we'll have to do is link the corresponding vertical dashed lines with the associated temperature curves. And we note that the bottommost curve has an associated optimum that is to the right of that dashed line, which means that it is still a valid maximum efficiency for that temperature line. On the green line, though, this is where we start to constrain our system. The green line originally was a little bit to the left of where we have that green dashed line drawn, and that constraint now defines the location of the new maximum efficiency for the temperature line. And in this case, this constraint, because it necessarily changes the location of the maximum efficiency, it is known as an active constraint. And then we go to the red line, and we see that a long time ago, the maximum efficiency for that curve was much to the left, around 0.3 pressure ratio. But now that constraint pushes us much further to the right. Same thing for the other blue curves. That's one way of looking at this problem. Now, I want to look at the heat added and the heat rejected curves. These are the associated contour lines for the temperatures that we saw before, with more increments between the maximum and minimum temperatures. And I want to impose two constraints, not just one as we did before, and that was a very simple graphical problem to solve. I want to impose a constraint of about 3,300 maximum heat addition, and I want a minimum heat rejection of 1,800. Maybe there's something, it has something to do with the boiler on the Q added side. Maybe there's something to do with the condenser on the Q rejected side. Let's just put these constraints and practice these terms and practice these concepts. Now, the second way of solving a problem like this, and in this case with two constraints, is to go into our simulation and search exhaustively through each one of the pressure ratio and inlet turbine temperature combinations to see which ones have associated Q in and Q out that still remain within the feasible regime. And that's what I did in this case. This is the resulting efficiencies you have here are the ones that made the cut, if you want to use that term. And what I want to do now is take you through a quick demo to see how I reworked the ideal reheat ranking cycle that we wrote a little while ago, and add a couple of lines just to show you a very quick and easy way of incorporating constrained optimization. And here we are in the MATLAB script that we wrote together in class several weeks ago, where we define the boiler pressure and the condenser pressure, and you see that I defined the pressure ratio range and the temperature inlet to the turbine range. What I've done in this case is just to show you the use of the command linspace in MATLAB, where linspace, open parentheses, your minimum on your range, then your maximum on the range, and then you have an input argument that tells the function linspace how many equally spaced increments you have between the minimum and the maximum. In this case, I defined that before as 20, so the P ratio and T in and T, the turbine temperature, are both going to have 20 increments in them. Then what I did was, for each of the output maps that I want, I assigned their size, the M by N matrices for the three outputs here, just so I could save time, so MATLAB could save time in reassignment. Finally, these are the nested for loops that we discussed before, and we wrote the function inside prob2, as you may remember. What I want to do is now look at what happens if I wanted to exhaustively search through all of my efficiencies and look at the associated Q added max and the Q rejected minimum. The 3300 is what we talked about before for the Q add max, 1800 for the minimum on the Q rejected. And now I'm going to set up the problem. I'm going to have 3 new maps that are going to come out. And the maps that are going to come out are of the size m by n, where it's P ratio, length P ratio, and length turbine temperature, inlet. And I populated that initially, all the 3 of these matrices with zeros, using the zeros command that we saw in class. And I did something a little strange here. What I did is I multiplied each one of these indices, the values in each one of these indices, by not a number. So if I were to plot these maps on a contour or on a mesh after all of these commands were entered, I would get nothing on the screen. And I do that for a special reason. I'll talk about it a little later. Now what I did was nested 2 for loops that allow me to go through each one of the indices, the combinations of indices, P ratio and TNT. And then I looked at what the associated rejected and added heats were, and I said that if the added heat is less than or equal to the constraint I had above, and this is the logical operator and 2 ampersands together, Q rejecteds are greater than or equal to the Q rejected minimum, then write all of the numbers that you have for efficiency, rejected, and added heat to a new map, the ones that I created earlier. Just keep all the good stuff. And then what I want to do is look at the associated efficiencies, and if the current efficiency is greater than the maximum efficiency that I have in my memory right now, F max, then assign the current efficiency to the variable F max. And by the way, while you're at it, give me the best temperature by looking at the current temperature, and then the best pressure ratio by looking at the current pressure ratio. So now not only do I know the location, but I also know the value of the efficiencies, and I can just dump those out to the screen later, which is exactly what happens down here, so that the user can see what's going on. So the reason I want to use not a number here is that these new maps that come out will have in them the associated numbers for Qs and for the efficiencies, and they're orders of magnitude in some cases away from 0. So what I want to do is just look at data that exists, 3-dimensional map that had these data plotted, and I had these artificial zeros on that plot as well. The plot wouldn't look very nice. So what I've done is gotten rid of them completely, so they're not printed at all. So what I'm going to have is a number of meshes down here that allow me to look at the resulting outputs, and what we'll do is just run this cycle. And as you can see, we have a number of meshes that are outputted to the screen, and we have these 3 outputs for the T optimum, the P ratio optimum, and the optimum efficiency that result from this constrained optimization case. What I'll do is I'll move these graphs to the side so we can look at all of them, and what we'll do is change the angle so we get a better view of these meshes. I'll start with the efficiency, figure 1. For the unconstrained case, and of course that's what we had before, but this time look, we have all of these efficiencies that didn't make the cut, that weren't good enough because they didn't fall within the feasible design space. And we see the associated Q rejecteds over here. We see the associated the heat added right there. And what I wanted to do is play a little trick over here. And you see the original graph, the original mesh that we have, figure 1 on the side over here. Well, what I want to do is superimpose this graph on the original to see where it really overlays. And I'm going to play a little bit of a trick. This is just for visual effect. I'm going to take the new map, the truncated one, and for each one of these I'm just going to add a little bit of efficiency, 0.001, and then I'm going to plot them on figure 1. I'm going to hold on that plot and mesh P ratio TNT new efficiency map. And so what I should get after I save this, and after I'll just cut and paste this into the console command window, is for visual effect I want to see exactly where that new map falls. And you see that we have really constrained that design domain a lot. But now what we can do is, well, the maximum efficiency is somewhere out here, right? I could increase the number of increments and have a finer and finer mesh and spend a little more time getting closer and closer and closer. And this is actually a very good method of trying to find the optimum in this situation with only these two constraints. Problem is, what happens if I have more constraints? Do I just keep going with this and augment my logical statements that I had before? Well, there must be a better way. So we've seen a couple of ways of optimizing. Optimize graphically. We could just use the exhaustive combinatorial search. So let's get back to the presentation, so we could start talking about these concepts. And as a quick summary, we started off with the unconstrained case, and we clearly saw that if we added constraints for the Q addition and Q rejection, we could do a pretty good job at finding the location of this optimum. Now, the graphical method, yeah, sure, it's not exact, but a lot of times you don't really need to have precise numbers. Question is, what happens if you do need precise numbers? Next, we performed this exhaustive search and we did a pretty good job. But what happens if you have many more constraints, which is many times this is the case? What happens if there are more variables? What happens if we changed all of the pressures and all the temperatures in the system? Well, it becomes computationally intensive, and a lot of times it becomes prohibitive. Remember that each one of the points that you solved on the plot took you about 2 hours to do by hand, and in the matter of maybe half a second we were able to get an entire map, hundreds upon hundreds of points. When you increase the number of constraints and variables, sometimes you can't really even visualize the outputs. So what I want to do is look at a beer can problem, which I think you've seen before. It's basically, let's take a beer can and minimize the material cost of the aluminum that's used in that can. I'm going to make a lot of assumptions here. First, here's your beer can on the side. It's cylindrical, and we have a number of knowns. I want to make sure that the volume of the drink is a given. Let's say it's 1 liter right now. And the can diameter, I'll signify that with B. The height is capital L. And the cost per volume of aluminum is little c. The sheet metal thickness, which I am going to assume is uniform throughout, even though this is not the case in the regular can. In fact, the aluminum on the top of the can is not the same type of aluminum that's on the sides. But we'll assume that they're all the same, that it's a uniform thickness, and that there is a total material cost associated with, and this is what we're trying to minimize. So after doing a little geometry, we formulate the problem, and we say that total cost is equal to the total volume of the aluminum on the side plus the total volume of the top and bottom aluminum caps in the bottom, and all of that is multiplied by the cost per unit volume. And when I look at this equation, I think, well, let me simplify this a little bit, because really the thickness is, we can factor that thickness out, and then we have a constant CT that is multiplied, and we could even take pi out. What we can do is eliminate the t to make this problem a little easier, so that we don't have so many variables, and we could eliminate c, because really, if you look at that function for the dollars, then it's just a multiplier. The location of the optimum is not going to change. Sure, the value of the optimum is going to change. It's a different function, but the location is not going to change. I'm just interested in the location. And these two will, once I've eliminated them, we'll just turn the problem into a surface area problem. Let's minimize the surface area on this can. The next thing we recognize is that there's an intrinsic relationship between the diameter of the can, its height, and the given drink volume. And if we use this equation where the drink volume is equal to pi b squared over 4 times the height, then we can extract and substitute this height into the main equation above, thereby making our objective function a function of only the can diameter. And so what we get once we perform these substitutions and simplifications is that we minimize the surface area of the can, 2 pi times b over 2 squared plus pi b times 4 times the drink volume divided by pi b squared. So we take this equation that we're trying to minimize, and this equation is subject to a series of constraints. First, we have the drink volume constraint, and then we have the upper and lower bounds for both the can diameter and its height. The drink volume constraint is known as an equality constraint, and the inequalities here are called side constraints on the variables. What we remember from our calculus class is that if we took this equation, this minimization, this objective function that we're trying to minimize, we take the first order derivative, we get pi b minus 4 times the drink volume b to the negative 2. If we set that to 0, we know that we get a stationary point. And once we solve for the can diameter, we get this equation. The quantity of 4 times the drink volume divided by pi, all of that raised to the 1/3 power. Then we remember that if we take the second derivative of that objective function, in this case it's going to equal pi plus 8 times the drink volume times the can diameter raised to the negative 1/3 power. We realize instantly that this equation is always going to be greater than 0. And what we remember from calculus is that if the second derivative is greater than 0, that's almost like being inside a well, where everywhere you look around you, and that's what the second derivative means, is everywhere around you is looking upward. So we know that this stationary point is now at least a local minimum. For optimality to occur, in other words, for you to be ensured that you have a local minimum, you have to test it with the first derivative, and if it passes the first test, this is called the necessary condition. And if it passes the second derivative test, where the second derivative is always greater than 0, then it's sufficient that it is at least a local minimum. So from before, let's keep going with the solution. The diameter is equal to this. We know that the height is equal to this equation from our substitution way at the beginning, and then we just substitute into the height equation, and if we reduce, we instantly see that the diameter and the height are identical, which means that if you looked at a side view of this can, it would have a square aspect ratio, which is a very important issue here. Why isn't it that the cans that we drink our beverages out of, why don't they have a square aspect ratio? And that has to do with the constraints of packaging and also of what people like to hold in their hand. The real reason that I'm showing you this problem isn't because of my affinity for beer or any type of beverage. It's really because this is the first problem you solve when you look at the heat transfer losses from an internal combustion engine, the type that we studied during the first module of this course, if you minimize the surface area to volume ratio there, then you also tend toward minimizing the heat transfer to the wall, and thereby you increase your efficiency. Now, that's almost like a first-order solution to that problem, if you want to think of it that way. There are a lot of nonlinear effects inside the combustion process and inside the engine combustion chamber, and so in modern engines you don't necessarily have a one-to-one bore to stroke ratio. In fact, that's why I used B and L, because those are the standard variables for bore and stroke respectively. You see that because of combustion effects, because of emissions effects, fluid dynamics inside the cylinder, and different combustion speeds within the combustion chamber at different times, you don't get necessarily a one-to-one bore to stroke ratio, but it's close. That's a starting point. So I want to go and generalize this procedure where we look at the first order and second order conditions, and in the first order, for just one variable, we just find the derivative of that function with respect to that variable, and we set it equal to 0, and we solve. For the second order, d squared f divided by dx squared must be greater than 0. Ensure that it's not greater than and equal to 0. It's strictly greater than 0. I want to extend this to multiple dimensions. And on the right, we have the del of f is equal to df by the partial of f with respect to x1, and we fill out this column vector until we get to x sub n. For the second order condition, we develop this matrix where we have d squared f over dx1 squared. We fill out this matrix. Remember that the on this row, d by dx1 of df dxn, and at the other end of this diagonal, we have d squared f over dx and squared in this square matrix. This is called del squared f. This is also known as the Hessian. And what we try to do is find out if this Hessian is greater than 0. This condition is known as positive definiteness. And in order to do that, we find out all the eigenvalues, and if the eigenvalues are positive, it's known as a positive definite matrix, Hessian matrix. So let's look at the constrained case where, let's write this out and generalize, where we try to minimize a function. That function is a function of x. That x and that twiddle under the x means that it's a vector. There are multiple x's, x1 all the way up to xn, and they're all real numbers. This function is subject to inequality and equality constraints. Inequality constraints are denoted as g of x less than or equal to 0. And I have to note that everything that you have on this side of the equation, bring it to the left side so that it's less than or equal to 0. This is the standard notation. And same thing goes for the equality. Bring everything that would have been on this side of the equation, the right side, all the way to the left side. And this h of x is equal to 0. And this form is known as negative null form. I want you to look at this g vector, which is just a vector of the different constraints that may exist. The number of constraints has nothing to do with the number of variables, and we go from g1 to g of x, and these functions themselves don't necessarily require each one of the variables. I want you to remember that each one of these functions, both the inequality and equality, don't necessarily need all of these variables. They could pick and choose. They could use all of them, but we have to make sure of that we understand that. And finally, we have the upper and lower bounds on each one of the variables in that vector. Let's keep generalizing. Now, we looked at the unconstrained case before and we solved that problem with the beer can, but here's the problem. What happens if you do have constraints? Wouldn't it be nice if you could come up with an equivalent function that is a function of your objective, plus it penalizes that function if there is a violation on each one of the constraints. Let's think about that. If you want to minimize something and you add on a penalty, that means it looks less attractive when you're optimizing it, so you stay away from it. The more and more you violate the constraints, the less and less attractive that point that you're investigating is. And so in order to do this, you've probably done this in your calculus class. You look at the original function, and for your inequality constraints, you multiply them by what's known as a Lagrange multiplier. And this Lagrange multiplier has something to do with gradient information inside the design space. These Lagrange multipliers, as I've noted here, I equals 1 to k, these are for the inequality constraints. And for the equality constraints, we have j equals 1 plus k to k plus m. And I've noted them this way so that we can distinguish between the different lambdas, these Lagrange multipliers. And this function, this equivalent function, is known as a Lagrangian, which is what we're going to look at now. And if that's the equivalent function, then what's the equivalent first derivative of that function, or the del of that function? Well, we look at the gradient, this del of f, plus the Lagrangians multiplied by the gradients of the respective inequality constraints and then the equality constraints. And for the second order condition, we do the same. Del squared f plus all the lambdas times the del squareds of the constraints. And so what we're doing here is we're developing a Jacobian. It's known as a Jacobian for the equivalent function, the Lagrangian itself. And the second order derivative of that matrix is known as the Hessian. Remember, again, that's the Lagrangian that we're looking at. Just the L is the Lagrangian. Now, if we're looking at the sufficiency condition, the second order condition, where we need a positive definiteness of that Hessian matrix, we have to make sure that all of the Lagrange multipliers that are linked to the inequality constraints have to be strictly greater than 0. And this makes sure that you're on that side of the constraint. Meanwhile, for the inequality constraint, there's no restriction. They could be, for the equality constraint, there's no restriction. You can be on either side, and you try to minimize that Lagrange multiplier. So before we begin with MATLAB, and that's what we're going to do next, we're going to have a demo in MATLAB in optimization. I want you to think about what an iterative design process means to you. And so what I want to look at now is generalized iterative schemes. And what we do is we develop the next iteration in an iterative scheme. And that depends on where we are right now. What is the current design? Plus, we want to move a certain distance away, alpha, from that original design, multiplied by a direction. So that's what this means. This means that if we started at xa, we get a certain function. Depending on our knowledge of the design space at xa and f of xa, we develop a search direction. Which way do I go? Do I go this way? Do I go that way? Do I go that way? And we also develop a scalar step. How far away from that initial design do we want to go? And so that's what we're going to do now in this beer can demo. Where we go into bopt intro. That's the bopt intro folder, and it contains a number of subfolders. I want to double click on the beer can, and what you'll notice is that there are a number of .m files. You may have some other files in there, like the nowf, which is an ASCII, or a .mat, which is a MATLAB file, or summary.txt, which is another text file. I just want to look at all the .m files for now, and why not just open them all up? Open up const file, which contains the constraints of our problem. Func file is the function file. This is the objective function. Master opt is the file that controls all of the optimization that's going on. It's the one that you go to define the problem, to define the parameters and the limits on the variables, and to define things like termination criteria and convergence criteria. Then I want to open plot history and plot my data. I want to start off with master.opt. And in this file, we see that we clear everything in the workspace at the top, and we have a couple of comments that tell us that x1 is equal to diameter and the height is equal to x2. This x array, x1 and x2, will be sent to our function file. Let's go quickly over to that func file. And what happens here is that the function outputs a variable f is equal to func file x. So this x is x1 and x2. It's fed into this equation. Once this function is done, it delivers f to the calling function. What I've done down here in this func file is also, just to practice the use of saving in ASCII format, is to save to a file called now_f. In that file, we save the objective function in ASCII format, and this is the MATLAB convention for that. Let's go back to the master opt file, and in here we scroll down, and the first thing you see after the comments is that we delete the 3 files that I mentioned earlier. These 3 files exist there because they are remnants from a previous optimization. And then what I do is I define my constraint, the drink volume constraint. Next, what I do is I define the initial design, where x1 is my starting point, and I've defined that as the can diameter being 7.0 centimeters and the can height being 11.0 centimeters. The next array defines the lower bounds, the associated lower bounds for both my variables. Here, both the can diameter and the can height are at 7. The upper bound to my diameter and to my length are 10 and 12 respectively. I save all of the numbers above that I've defined into a file known as run specs. I save lower bounds, upper bounds, the volume constraint, and the initial design. Then what happens is we define a series of options, and these options are delivered to the fninCon function in a couple of lines. Let's go into these options. We have tol_x, tol_fun, tol_constraint, that's what tol_con means, maximum iterations, diff_min_change, diff_max_change, large scale, and off. I really want to target these tolerances and these diff changes. The tol_x, these tolerances are really convergence criteria. They say that if your x function or constraint don't change by more than these associated numbers, then you've converged. Don't go any further. The user doesn't want any answers that are more precise than that. Max iterations, we'll go into a little bit. It's not necessarily what you think it means. I'll show it to you once we run the optimization. Min diff changes. Diff min change is what you're allowing the optimizer, how fine a step size you're allowing the optimizer to go from that original step. So, and max, the diff max change is the maximum step. Let's talk about these steps a little bit. What do they mean? Well, what they mean is that if you're at an initial design, you're going to perturb each variable successively by a certain amount. And you don't want to step too far away, you don't want to step too closely, you want to make sure that you're stepping far enough so that you capture the dominant slopes, basically, inside your design space. And so you perform one function call, you perform the call at x1, you perturb the diameter perform another function call, see what that function is. Then you reset the diameter back to 7, but this time you change 11 by the amount that's defined down here. So now you're changing them orthogonally, and now after 3 function calls, you have some gradient information at x1, and from that gradient information, the optimizer calculates the constraint violations, it calculates the functions, it uses derivatives to find out what the next iteration is going to be, what the next set of x values is going to be, and then it continues from that point on until it reaches these termination criteria or the convergence criteria. After these options have been defined, we just put onto the screen, we're telling the user, hey, the optimization is running. We invoke the fminCon function here, which requires it to tell you to tell it, here's the function file, this is what it's called, make sure that it's in this directory, here are my initial x1 numbers, my lower bound, my upper bound, my constraint file, and all the options you wanted from me. And after it's done doing what it's doing inside this one line, it delivers xopt is equal to something onto your screen. The other 2 commands in this file are plot my data and plot history. We're going to go to those soon. We've talked about function file. This is where the function resides. And here we have the constraints file. The constraints file is called const file, and it takes in the x vector. At the beginning, I load run specs and now f, because run specs contains my volume constraint, and now f contains the function call. There's no communication between the const file and the func file otherwise. Then I have a set of inequality constraints. There are no inequality constraints in this case, so my C vector, which contains the inequality constraints, is null. Now I'm going to do my equality constraint. I find that my current volume, my vol, is equal to 1/2 pi x1, which is the diameter squared, times the height. That's the current volume using the current design iteration numbers. I take my vol and I find the difference between it and volcons, volume constraint, which I defined in my master opt file. This volume constraint came from run specs after I loaded it. My CEQ1, this is just like saying H1 when we were generalizing. The CEQ1 is the difference between these 2. And that's the only constraint, the only inequality constraint, the only equality constraint on the system. Now from this point on, MATLAB doesn't need any of this, but I really need this, because what happens is many times optimizations take a very long time to run. They could be milliseconds, they could take days. What I want to do is I want to write a file that outside of MATLAB I can take the file, open it up, and see what the optimizer is up to. And by doing this, I can see if the optimizer has gotten into an infinite loop, and preemptively stop the simulation if need be. Now, what I do is I open up a file called summary.txt. What this letter here, A, stands for, is it means that I'm going to append to the text file. And in that text file, I write each one of those variables, the current design variables. Then I write, on the same row, I write the current function, the objective function value. And finally, I go through all of my equality constraints and write them down. In this case, we only have 1, so it just writes that down. Finally, it goes to the next line. It just presses enter, basically, so that when you, after you close the file and then reopen it again, you're on a fresh line for the next data point. Okay, so we have the const file, we have the function file, we have master opt, and we said that we had two last functions in master opt. One was plot my data. So let's look at plot my data. And what it does is it starts by clearing everything, loading the summary and the run specs, and then taking the upper and lower bounds with user-defined increments, and it uses the data from the optimizer, from the summary text file, to plot the history of the optimizer with regards to diameter and the length on a contour plot, which is defined by these constraints here. You sent these constraints to it, and we calculate, after we define the ranges, the volume and the surface area. And what we're going to do is we're going to overlay the contour plots of the volume and the surface area and use all the data from the optimization run to see what the optimizer was doing. What we're going to do is only keep the volume level for the 1000 cc problem, or the 500 cc, whichever. You know, we can go back to master op and change that. That's not the point. And what we have in figure 5 is a contour plot of the volume, a contour plot of the surface, but the volume, remember, this contour plot has a handle over here where we're only going to plot the very close to the volume constraint. Okay? And so at the end, on top of that contour, we plot the summary of the x1 and x2. And finally, the last plot file, plot my data subroutine, takes the summary.txt, finds out how big it is, and then plots things accordingly. In other words, what it's going to do in different figures is it's going to individually look at what happened with can diameter, what happened with can height, surface area, and max constraint violation. We want to see what the optimizer is doing, because that gives us a lot of insight as to how well the problem has been formulated and how well we've defined things like the tolerance criteria and the diff change and the max iterations. Okay, so you know what I want to do is now go back to master opt, and let's try to run this program. Remember, we have a volume constraint of 500 cc. That's half of what we had in our class problem. That's no problem. And we're going to start this optimization at a can diameter of 7 centimeters and a height of 11 centimeters. Let's make sure that everything is saved. Right, everything is saved by looking over here, and the save all button is grayed out, so we're fine, we're ready to go. I'm going to go into my command window. Master opt is the function that we press enter, and look at all these graphs that came to the screen. Let's put all these graphs down for a second. Let's iconify them, and I want to look at what's going on with this optimization. First, the first column on the left, we have iteration. 0, 1, 2, 3, 4, 5, 6. F count is the function call. How many times was the function, func file, called for each one of these iterations? The first iteration, which is iteration 0, called the function 3 times. In other words, the initial design and then the 2 different perturbations from that initial design. So 2 steps for the diameter and then for the height. And you see that's how it progresses throughout the process. And on the 7th step, we have 21. So each one of these steps had 3 different function calls so that it can gain some directional derivative, some type of gradient information. And then f of x is just the function call value that we have at that step. And this is the objective function. This is what we want to minimize. The max constraint violation is just that. It's the constraint, and what we see is that this maximum constraint is decreasing as we go. The line search step length is something we haven't talked about. It just tells us that what I see here is that each one of these is a step length of 1, which means that the optimizer didn't have to do any real thinking. It saw all of these derivatives as it was calculating them, and the design space was very, very smooth. So it didn't have to do things like half steps or quarter steps and then use that information to better understand what's going on in the landscape of that feasible design space. Directional derivative, we want this to be as small as possible. And then first order optimality, these are other conditions that we haven't defined yet. Procedure, infeasible start point, we started off well in the infeasible regime, and we see this Hessian modified at the end. Why is the Hessian modified? Well, the thing is that as it's progressing, it has memory, and it says, well, after these first 2-3 iterations, this is my approximation of what the design space looks like. And as it gains more and more information in the design space, it has to go back and modify the Hessian so that it knows better how to go to the next step. Okay, so at the bottom of this we see xopt is equal to 8.6026 and 8.6025. In engineering terms, these are identical diameter and length, and we see that there are no active inequalities because, well, we didn't have any inequalities. So let's start looking at functions now, figures now, and the first figure tells me what the optimizer was doing with can diameter. It was varying it from the initial 7, then you can't see it right there, but if you zoom in you see it perturbed a little bit, got some information, jumped over here, perturbed a little bit, then jumped back, and then found almost like a steady state, a little bit over 8.6. We go to figure 2, and this is what it did with the height. It started at 11, jumped down the same time that it jumped up with diameter, and then ultimately converged to 8.6. Figure 3 shows us what happened with the surface area. The surface area had to increase because our constraint was being violated so much. So let's take a look at that constraint. And so it started well in the infeasible regime, and it got closer and closer and closer to being 0. Okay, so that equality constraint was active. It was riding right on that equality constraint. And the final figure shows us, and I'll zoom in on this, it shows us a couple of things. First, all of these contours that you see going from blue all the way to red on this side of the graph, these are the surface area contours. And these two lines that you see right here, and I did that specifically to draw attention to this contour, is right in the neighborhood of 500 cc's. I put these two lines together with that V array, that argument that we sent to the contour function in the one of the plot files. And then you see this magenta line where we start at a can diameter of 7 and a height of 11, so that's our starting point. And after it took its information from this point, it jumped all the way to this point. And after that iteration, it jumped here and there and there and there until it converged right on that equality constraint and at the location where the can height and the diameter are exactly the same. I want to zoom in at that initial point, if I may, just so that you can see something. Zooming, 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 zooming. And here you'll see that initial step. It started at 7.11. It stepped over, just the can diameter was changed to 7.0001. And then the third step was keep the diameter the same at 7, but now change 11 to 11.0001. Once it got information on the constraints and the function from that point, it was able to go to the next step. And each one of these crosses, you don't see them here because we're so far away, is exactly what you saw there, 3 points. Okay.